Hello friends, you are watching Civil Engineering Study and Construction channel. I am Devesh Bhattacharya is here with you again with a very important video. My today's video is on the detail of reinforcement of RCC beam and RCC slab. Friends, reinforcement is the backbone of any RCC structure. If reinforcement is wrong, even the best concrete will fail. What you are watching here in this video, this is the proposed construction of a RCC roof slab where reinforcement for beam and slab have been binded. In this video, I will explain reinforcement of RCC beam and slab for roof slab step by step, strictly as per Indian Standard Code of Practice. We will understand specifications of reinforcement steel, the function of each bar in beam and slab, and the basic concepts of bending moment, shear force and stresses without discussing concreting work. This video is extremely useful for civil engineering students, site engineers and anyone involved in RCC construction. Friends, before understanding beam and slab reinforcement, we must know the specification of reinforcement steel used in RCC work. Reinforcement steel shall be HYSD bar, that is high strength deformed bars. Common grades are Fe415, Fe500 and Fe500D. D means better ductility, which is preferred in seismic zone work. Indian Standard Code of Practice 1786 may be referred for the specification of high strength deformed steel bars. The yield strength for Fe415 is 415 Newton per millimeter square and Fe500 equal to 500 Newton per millimeter square. Higher grade means higher strength, but ductility must also be ensured for seismic zone work. Deformed ribs improve bond strength between steel and concrete. Plain bars are not recommended for RCC structural members. Clause number 26.2.1 of Indian Standard Code of Practice 456-2000 may please be referred. As per Indian Standard Code of Practice 456-2000 and clause number 26.4, the cover for slab equal to 15 mm of or bar diameter, whichever is more, and for beam this is 25 mm. So friends, first I am going to discuss the function of the reinforcement of a beam. Beam is a flexural member. There are 5 reinforcement components in a RCC beam. Number 1, bottom longitudinal bars. Number 2, extra top bars near support. Number 3, top longitudinal bars. Number 4, stirrups, and number 5 is development length of bar. Now stating placement and function of these all bars step by step. Number 1, bottom longitudinal bars. In case of simply supported or continuous beam, the maximum positive bending moment or maximum sagging bending moment occurs at the midspan of the beam, causing tension at the bottom fiber of the beam. Hence, we have to provide main longitudinal reinforcement at the bottom of the beam. The quantity of the bottom reinforcement will be according to the magnitude of the positive bending moment. Now, friends, see in this video that at bottom of the beam there are 2 numbers or 3 numbers, or somewhere it is 4 numbers. 16 mm dia longitudinal bars have been provided. The number of bars varies due to the varying magnitude of positive bending moment, which depend on the span of the beam and coming load on the beam. Now second reinforcement component, that is extra top bar near the support. The maximum negative bending moment or maximum hogging bending moment occurs near the supports of the beam, causing tension at the top fiber of the beam at those zones. Hence, we have to provide additional reinforcement at top near the supports in addition to the top longitudinal bars. The quantity of this top extra bar will be according to the magnitude of the negative bending moment. See in this video that at every support of the beam there are 2 numbers or somewhere 1 number 16 mm dia extra top bars have been provided. Now stating the third reinforcement component, that is top longitudinal bars. At top, in the midspan of the beam, compressive stress occurs. In normal condition, Theoretically, there is no reinforcement required and concrete itself is sufficient for this compressive stress. But for the stability of the member and as a hanger bar of the stirrups, at least 2 longitudinal bars are required to provide in the top layer of the beam. Now going to the fourth reinforcement component, that is stirrups. In RCC beam, stirrups, which is also called as shear reinforcement, are critical for resisting shear forces and holding the longitudinal bars in place and provide additional strength to the beam. Their shapes like closed loops of rectangular or square. Their specification, spacing and design are guided in table number 5 of clause number 26.5.1.6 and 26.5.1.7 of Indian Standard Code of Practice 456/2000. In construction, stirrups are critical for ensuring the strength and stability of RCC beam under various loads. Friends, there are several important functions of these stirrups. I am stating here at least 4 very much important functions of these stirrups. Number 1, it resists shear forces and prevent diagonal cracks caused by these forces. They are particularly critical in areas near the supports of a beam where shear stress is maximum. Number 2, stirrups holds main reinforcements in place and ensures that the main longitudinal reinforcement bars remain in their correct position during construction and concrete pouring, maintaining the beam's structural integrity. Number 3, stirrups improved the ductility of the beam and ensure that the concrete in the core remain confined, which enhances the beam's capacity to absorb energy and deform without failure. Number 4, stirrups help in controlling crack propagation under loads, improving the overall durability and lifespan of the structure. Stirrups are typically spaced closer together in areas with high shear stress and further apart in regions with lower shear stress following design guidelines. Generally, this is close near the supports and apart in the midspan of the beam. Now some additional important points on this stirrup. As per clause number 26.5.1.1 of Indian Standard Code of Practice 456/2000, the minimum dia of bar in stirrups is 8 mm, and if the span of the beam more than 5 meter, then it is 10 mm dia. The 135-degree hook in stirrups is mandatory as per clause number 5.1.1 of Indian Standard Code of Practice 2502/1963 and IS 456/2000, which serves critical structural purpose. The 135-degree bend followed by 10D extension ensures the stirrup does not slip or pull out under shear or torsion stress. This anchorage grips the concrete much more effectively than a 90-degree bend. When a beam is loaded, shear force tends to open up the stirrups. The 135-degree hook resists this opening action better than 90-degree hook, providing mechanical interlock and preventing early failure. In seismic zone, beams undergo reversing stresses. 135-degree hook helps to keep stirrups firmly engaged, avoiding unzipping of the ties under shaking and then improving ductility and confinement, which improves earthquake resistance. The maximum spacing of stirrups should be as per clause number 26.5.1.5 of Indian Standard Code of Practice 456/2000. This is 0.75 into effective depth of the beam or 300 mm, whichever is less. For torsion member, it should be as per clause number 41.4 of Indian Standard Code of Practice 456/2000. This is less than equal to 0.75 into minimum dimension of the beam but not more than 300 mm. Friends, see this beam. This is cantilever beam. It is one end fixed and another end is free. In this case, the hogging bending moment occurs at the top fiber of the beam, resulting tensile stress generates at top of the beam. To resist this tensile stress, we have to provide the main reinforcement at top of the beam, and quantity of this reinforcement will be according to the magnitude of negative bending moment. Here in this work, 4 numbers 16 mm torch steel bars have been provided at top face of the beam as a tensile reinforcement, and at bottom there is 2 numbers 16 mm bar only. Theoretically, at bottom there is no need to provide any reinforcement, but for the stability of the beam and to fix the stirrups and to control the temperature and crack, the minimum bottom reinforcement is to be provided. Hence, here 2 numbers bars have been provided. Now number 5 reinforcement component of beam. This is development length of bar. Development length is needed to be provided at both end of all the longitudinal bars of top and bottom of the beam. Friends, I have seen at many construction sites that this point is simply ignored, which is a highly incorrect practice of work and unsafe for the structure. Friends, see in this video that unfortunately here is also it is ignored and not provided this development length in a single bar, whereas all the bars at the end should have been sufficiently extended in the form of L. I am stating here what is the development length and what is the necessity to provide of this development length. Development length in a beam is a required length of reinforcement bar that needs to be embedded to concrete to effectively transfer the stress between the steel and concrete. This is crucial for ensuring beam's structural integrity and premature failure, especially at the beam column junction. Without sufficient development length, the rebar may be pulled out of concrete under load, leading to structural failure. The required development length is influenced by several factors, including the dia of rebar, the type of steel, that is HYSD bar or plain bar, the concrete grade and stress in the strail. Friends, as I told earlier that all the longitudinal bars top and bottom should be extended at both the end in the form of L shape, upward or downward. This L shape part of the reinforcement is called development length. Friends, unfortunately it is seen in many videos that the creator of the video is stating that the development length is to be 10D or 20D or 25D, etc., etc. But friend, this is absolutely incorrect and wrong practice of work. There is no such thumb rule. If we accurately predict this development length, we have to follow the clause number 26.2.1 of Indian Standard Code of Practice 456/2000, which stated the formula to find out the required development length. Listen one thing, why I have said that thumb rule for development length is not applicable. Because in every case the length differs as it depends on the dia of bar, different value of stress in different type of steel bar and different grade of concrete used. However, according to IS 456/2000, the development length LD equal to phi into sigma s divided by 4 tau BD, whereas LD equal to development length, phi equal to dia of reinforcement bar, sigma s equal to stress in a bar at the point considered at the time of load design, and tau BD equal to designed bond stress. Though the formula works for both the working stress and limit state method of design, but the value of designed bond stress is different for each. So friends, development length is a key element where it comes to steel design in construction. So friends, these were all about the moment, shear and stresses in the reinforcement of beam. Now I am going to the detail of the reinforcement of slab. Like RCC beam, RCC slab is also a flexural member. Stating the structural behavior of a slab. For simply supported or continuous slab, the maximum positive bending moment or maximum sagging bending moment occurs at the midspan of the slab, causing tension at the bottom fiber of the slab. Hence, main reinforcement is required at the bottom face of the slab and quantity of reinforcement is to be according to the magnitude of the positive bending moment. Further, the maximum negative bending moment or maximum hogging bending moment occurs at the top of the slab near supports, causing tension at the top fiber of the slab near supports. Thus, near supports, main reinforcement is required according to the magnitude of negative bending moment. In such case, every bottom alternate bars, main bars, may be taken at top near supports by cranking, and in between these two bars, extra piece of bars are provided at top as extra top bar. You please see in this video that every alternate main bars have been taken at top by cranking to cater the negative bending moment. See also in this video that distribution bars have been provided here perpendicular to main reinforcement bars. These bars control shrinkage, temperature stresses and distributes load uniformly. So friends, as I told earlier, as the slab acts as a flexural member, the maximum positive bending moment is at midspan and maximum negative bending moment is at support. Maximum shear force also occurs at supports. For deflection control, as per IS 456-2000 clause number 23, span to depth ratio of slab should not exceed 20 for simply supported slab and 26 for continuous slab. For crack control, reinforcement spacing should not exceed 3D or 300 mm, whichever is less. As per IS 456-2000, the minimum reinforcement for slab is 0.12% of gross cross-sectional area of slab for HYSD bar and 0.15% for mild steel bars. In case of slab of normal depth, shear stress is usually registered by concrete. If the normal shear stress exceeds tau c, shear reinforcement is added as per table 19 of IS 456-2000. As per IS 456-2000, minimum cover for slab is 15 mm or bar dia, whichever is more. In slab, for controlling shrinkage, temperature stresses and load distribution uniformly, distribution bars are to be provided perpendicular to the main reinforcement bar. So friends, this was the complete and detailed explanation of laying reinforcement in RCC beams and slabs, including the function of every reinforcement bar, structural behavior under loads, bending moments, shear forces, development length, etc. as per Indian Standard Code of Practice. I hope this detailed session will greatly help you in site execution as well as for civil engineering students. If you found this video useful, please like, share and subscribe this civil engineering study and construction channel. Please press the bell icon for regular technical videos. Thank you for watching this video. See you in the next class. Thanks.